readers that
Well, we'll start in a few minutes, just giving people a little bit more time to get on. Yeah, I can ask you questions about any material you have in the lectures or in the text or from the homework. What can I do for you? This is a updated lecture and homework schedule, which I will email to you and post on Blackboard right after class ends. So the most interesting thing, though, that's the following. So let me just first write this down. So this is Math 424 and something else, PDE, Lecture 5. So if you've taken calculus at Lehman, you will have, along with calculus, taken the calculus lab, which uses some software, a mathematics computer program called Maple. And every year now they come out with a new version. The current one is Maple 2020. And I posted on the Blackboard website for the class, and I also emailed you instructions about how you can download Maple for free from a CUNY website. So if you needed to buy it, it costs a couple $100, I think, but you get it for free as a CUNY student. And we are going to use some of Maple to solve some differential equations. That is, it's a little bit ridiculous to take a course in ordinary or partial differential equations where you do everything by hand, because you can only do relatively simple problems by hand, and problems that come up in mathematics and physics and elsewhere, and where mathematics is used, financial modeling on Wall Street or predicting the weather and so forth, are 99% solved by computer programs. So Maple is excellent, and it's free. So if you don't have it, you can get it for free. The only thing you have to be careful about when you get it is not reading the instructions on the CUNY website carefully. It may require, when you install the program, it might require some secret number that you type in, and it's not very secret. It's there on the CUNY website. You just have to make sure you don't ignore it, but you write it down. So when you install the program, you actually can install the program. So how many of you, you can just tell me by chat or whatever, have used Maple previously?
I've used it. Not often, but I've used it.
Just a long time ago in calculus 2.
Okay. So, so I will explain online how to use it, especially how to use it to solve a differential equation. And also on the YouTube channel for my math classes, I'm teaching Math 156, which is a Maple lab right now. And I post all the classes. So that is teaching from the very beginning how to use Maple. The only problem is that we've only had 2 classes so far, and we won't get up to how to do a derivative and an integral for a week or so. But in any case, at the point at which we start to use Maple, I'll devote a class to showing you how to use the software, or refreshing you on how to use the software. I mean, it's a valuable thing to know. There are several competing computer algebra mathematics programs on the market. There's Maple, there's Mathematica, there's MATLAB. The best ones actually are free, but they're harder to use. Maple is easy to use. Okay. Any questions or any problems you'd like me to go over? So I think according to the lecture and homework schedule, there's homework due on Wednesday on page 328, which is solving linear second order homogeneous differential equations with constant coefficients. And I'm happy to do some, and I'm happy not to do some. Okay. If not, then oops, interesting. So when I look at my notes from our last class, which was lecture 5, I spent some time doing some problems from the first homework set. And sometimes looking at these homogeneous differential equations, constant coefficients. Yep. But I did not yet look at the non-homogeneous case. So that is what I will do today. Okay. So we are looking at second order linear differential equations with constant coefficients. So y double prime plus ay prime plus by equals, in the homogeneous case, 0, and in the non-homogeneous case, some function r. So this is homogeneous if r is 0, and non-homogeneous if r is not 0. And let me just review what we've done already. So we looked at the homogeneous case, r equals 0. And then our differential equation looks like y double prime plus ay prime plus by equals 0. Okay. And there was the special case when a is 0, and then the differential equation is simply y double prime plus by equals 0, where b is some real number. And we saw that the solutions take 2 forms, or 3 forms, depending on whether b is positive, negative, or 0. So in the first case, when b is 0, we have y double prime is 0. And if y double prime is 0, that means that y prime is some constant, just by integrating. And if y prime is a constant, we know that y is a linear function. And if y is a linear function, y prime is a and y double prime is 0. So in the case b equals 0, we've proved the uniqueness and existence and a uniqueness theorem right here. In the case b equals 0, every linear function, sorry, I shouldn't have called that b. I should have called that, just use different letters. So y prime is some constant c1, so y is c1 plus a constant c2. So any linear function is a solution, and every solution is linear. So if there is a solution, it must be linear. So this is the uniqueness. Every solution is of this form. In case 2, let me just use the same order that the book does. B is positive or negative. Which one was case 2? B is negative. So if B is negative, you can write B as minus a positive number, and every positive number is a square. So then our equation is y double prime plus by, or y double prime minus k squared y equals 0, which means y double prime is k squared y. And one solution is u1 of x equals e to the kx, and another solution is u2 of x equals e to the minus kx. And it's straightforward to check. You differentiate once, you get k. Differentiate again, you get a k squared. That these two functions are solutions of this equation. And so a general solution will be u1 of x equals some constant times e to the kx plus another constant times e to the minus kx. So what I have here is an existence theorem. If b is negative, then there exist these exponential functions e to the kx and e to the minus kx. And if e to the kx and e to the minus kx are solutions, this linear combination of those two exponentials also is a solution. So this is an existence theorem, that there exists a solution. It's not a uniqueness theorem. We have not proven that there are no other solutions. We've only proven that these are solutions, which is pretty good, but it's existence and not uniqueness. What is case 3? Well, case 3 is, let's see, the first case was when b is positive, is 0. The second case is when b is negative. So this has to be the case b is positive. So b is equal to k squared for some positive number k. And our equation, y double prime plus by, is y double prime plus k squared y equals 0. And it's easy to check that one solution is u1 of x equals cosine of kx. Another solution is u2 of x equals the sine of kx. And a general solution is u of x equals any constant times cosine of kx plus any other constant times the sine of kx. So given k, b is equal to k squared, for any constant c1 and c2, we have solutions of the differential equation. Right? Okay. So again, this is an existence theorem. Given this differential equation, there exist solutions of this form. It's not a uniqueness theorem. Okay. So let me just insert one remark. In general, so the general homogeneous linear ODE, ordinary differential equation, is y double prime plus some function of y. I'm not sure what notation to use for that. Let me, well, let me just, well, let's say a of x times y prime plus b of x times y equals 0. So we can introduce what is called operator notation. So for every function f, define L of f. So L applied to the function f is what would you get? You would get if you plugged into the left-hand side of this. F double prime of x plus a of x, f prime of x plus b of x, f of x. Okay. So that's just this symbol, L of f. Apply. It's just like a function of a function. So this differential equation can be written as L of y equals 0. Why is that? Because L of y for a function y is y double prime plus a of x y prime plus b of x y equals 0. That's this differential equation. So this is just shorthand notation for the differential equation. It's very useful and it's used in mathematics all the time. Okay. And for a homogeneous linear differential equation, what linear means is the following. If u1 and u2 are solutions of the differential equation L of y equals 0, then what is L of u1 plus u2? Well, this means u1 plus u2 second derivative plus a of x times u1 plus u2 first derivative plus b of x times u1 plus u2. And they teach you in the very beginning of Calculus 1 that the derivative of the sum is the sum of the derivatives. So if you differentiate u1 plus u2 twice, you get u1 double prime plus u2 double prime plus a of x times, when you differentiate u1 plus u2, you get u1 prime plus u2 prime plus b times u1 plus u2. And I can just rearrange that. That's u1 double prime plus a of x u1 prime plus b of x u1. I've just used this term, and this term. Plus, and then what's left, I have u2 double prime plus a of x u2 prime plus b of x u2. And this is L of u1 and this is L of u2, which is 0 plus 0 or 0, because u1 and u2 are solutions of the differential equation. So what this shows is that if we have the differential equation, y double prime plus a of x y prime plus b of x y equals 0, and we define the operator L of y to be y double prime plus a of x y prime plus b of x y. If L of u1 and L of u2 are both 0, then L of u1 plus u2 equals 0. In fact, what this actually shows is, well, we actually proved that L of u1 plus u2 is L of u1 plus L of u2. So if both of these are 0, the sum is 0. And we also have the following. If we take a function u and multiply it by a constant c, L of c times u is cu double prime plus a of x cu prime plus b of x times cu. And this is cu double prime plus a of x cu prime. plus B of X CU. If I factor out the C, this is U double prime plus A of X U prime plus B of X U. That's C L of U. So these operator L satisfies L of U1 plus U2 is L of U1 plus L of U2, and L of CU is C L of U. And this implies, in general, that if you take L of C1U1 plus C2U2, this is what's called a linear combination of U1 and U2. This is L of the sum is the sum of L1 C1U1 plus L of C2U2. And you can take the constants outside the operator. This is C1 L of U1 plus C2 L of U2. So these two properties of this linear operator, this operator L, are important. Any operator that satisfies things like this are called linear. And if you took linear algebra, which I hope some of you at least did, then you're very familiar with linear operators. Any questions about this so far? Okay. So what we saw for the differential equation y double prime plus by equals 0, if b is greater than 0, sorry, if b is equal to some minus k squared less than 0, we can let u be c1 e to the kx plus c2 e to the minus kx. And for every choice of c1 and c2, we get a solution. If b is k squared greater than 0, we can let u be a linear combination of cosine of kx plus sine of kx. Now, in section 8.11 of Apostle, page 324 and 325, there is a uniqueness theorem. So our existence theorem says that for all constants C1 and C2, let me try and write this so it's legible. So the existence theorem says for all C1 and C2, this is a solution of this equation with negative b, and this is a solution of the equation with positive b. So solutions exist. Uniqueness says these solutions are unique. These are the only solutions that there are. And So the uniqueness theorem says exactly the following. So this is theorem 8.5. So let functions f of x and g of x satisfy the ordinary differential equation y double prime plus by equals 0 for all x from minus infinity to plus infinity. And suppose f of x, suppose at the point 0, f of 0 equals g of 0, and f prime of 0 equals g prime of 0. So if we have two solutions of this differential equation that satisfy this initial value condition, then, in fact, the solution is unique. F of x equals g of x for all x. So if you take this second order constant coefficient differential equation, if you have two solutions of the equation which take on the same values at 0 and their derivatives take on the same values at 0, then in fact f of x equals g of x for all x. So before I prove it, how does this show uniqueness over here? So suppose we have some function u of x equals c1 e to the kx plus c2, or sorry, so let me state it differently. I'll go to another page. So we have the differential equation y double prime plus by equals 0. B different from 0. And we want a solution u of x satisfying the initial condition u of 0 is equal to a. Sorry, I shouldn't say a. Not sure what letters to use here. What's a good choice of letters? Well, I'll use just capital A and capital B. That's a bad choice of letters. U prime of 0 is A, U of 0 is A, U prime of 0 is some capital B. Suppose that B is minus k squared less than 0. So I claim there exist constants C1 and C2 such that u of x equals C1 e to the kx plus C2 e to the minus kx we know it satisfies the differential equation. It also satisfies the initial condition. that means u of 0 equals A and u prime of 0 equals B. So how can I do that? Well, this is u of x, c1 e to the kx plus c2 e to the minus kx. And when I differentiate, I get k c1 e to the kx minus k c2 e to the minus kx. So when I evaluated 0, u of 0, well, e to the 0 is 1. U of 0 is c1 plus c2. And u prime of 0 is kc1 minus kc2. And I want to choose c1 and c2 such that this equals A and this equals B. Well, this just means solving two equations and two unknowns. If I multiply the first equation by k, I get kc1 plus kc2 equals ka. The second equation is kc1 minus kc2 equals b. If I add the equations, these cancel. I get 2kc1 is ka plus b. So c1 is ka plus b over 2k. And from this equation, c2 is a minus c1. So that's a minus ka plus b over 2k. And if I put that over a common denominator of 2k, I get 2ka minus ka. I get ka minus b. So if I did my high school algebra correctly, that says if I take the function u of x equals ka plus b over 2k e to the kx plus ka minus b over 2k e to the minus kx, we know this solves the differential equation. It's supposed to solve the initial condition. So if I evaluate this at 0, these are the exponentials are 1. I get ka plus b over 2k plus ka minus b over 2k. When I add, I get 2ka over 2k, which is a. So that initial condition checks. U prime of x, I multiply, I differentiate, I get a k. I get ka plus b over 2k times k. That just makes this a 2 e to the kx. When I differentiate this, I get a minus k minus ka minus b over 2k times 2, the k's cancel, e to the minus kx. So u prime of 0 is ka plus b over 2 minus ka minus b over 2, and I get 2b over 2 equals b. So this checks. So my differential equation has a solution, which is this linear combination of e to the kx and e to the minus kx for every choice of initial conditions. All right, good, very good. What about, yes, go ahead.
Can you just go up a little bit on the previous page slightly? Why is KC1 and the KC2 crossing out?
Here, this is KC2 and this is minus KC2. I'm adding these two equations.
Okay, sorry, because I don't know, I just saw those two diagonal lines, so I was just confused slightly.
No, so I said we're adding these equations. So this equation plus this equation, this gives me 2KC1, and this minus this is 0, so that's gone.
Okay, yeah, makes sense.
Okay. All right, and the other case, this was the case, oops, when B was negative. In the other case, we have, let's see, this is 6. That's supposed to be a 6. In the other case, we have B positive. B is equal to K squared. So we have the differential equation y double prime plus B plus K squared y equals 0. And we want to find the solution where U at 0 is equal to A and U prime at 0 is equal to capital B. And our general solution is U of X equals C1 cosine KX plus C2 sine of KX. U prime of X, when you differentiate, you get minus K C1 sine of KX plus KC2 cosine of KX. When you let X equal 0, we get U of 0. When you plug in X equals 0, cosine of 0 is 1. Sine of 0 is 0. Oh, so U of 0 is C1. So that has C1 has to be A. Here, when you plug in X equals 0, this is 0. And I get U prime of 0 is KC2. And that has to be B. So our general solution is U of X equals A times the cosine of KX plus C2 is B over K sine of KX. So we know this is a solution of the differential equation. Let's just double check the initial condition. When we differentiate, U prime of X is minus KA sine KX plus I get K times B over K cosine of KX, and the K's cancel. So when I plug in X equals 0, I get A. When I plug X equals 0 into the derivative, I get B. So for every choice of initial conditions, I can solve the differential equation using exponentials in the B less than 0 case and sine and cosine in the B greater than 0 case. So now I come back to the uniqueness theorem. So what we have to prove is, must prove that if f of x and g of x are solutions of the differential equation, so f double prime of x plus b f of x equals 0, and g double prime of x plus g prime of x plus b g of x equals 0, and f of 0 equals g of 0, f prime of 0 equals g prime of 0, then f of x equals g of x. That's the uniqueness theorem. You cannot have two different functions that satisfy the differential equation in the same initial condition. Now we just showed that if b is negative, there's always this linear combination of exponentials that solves the differential equation and any initial condition. So that's the only possible solution. And similarly, in the case b greater than 0, when you have sine and cosine solutions, you can match any initial condition with the right linear combination of sine and cosine. So that will be the only possible solution of the differential equation. I mean, so you have to understand why this proves that the exponentials and the trig functions give the only solutions of the differential equation. That's the uniqueness part. So the proof uses something from freshman calculus, namely the fact that you can expand a function as a Taylor polynomial plus the remainder. Now, to write a Taylor polynomial degree n for a polynomial for a function f, you have to know that the function has at least n different derivatives. Now, so this is a simple, but it's a little bit tricky point. You have to really think of this. So you have this differential equation. So f of x is a solution of the differential equation y double prime plus by equals 0. So y equal f of x can be differentiated twice, right? That is, if there is no second derivative, the function y, this means this differential equation has a solution f if f has a second derivative and the second derivative y double prime plus y satisfies this equation. Another way of saying that is, so if y double prime plus by equals 0, then y double prime is minus by. Can you differentiate y? Well, the third derivative, I'll just write this as y3, that's the derivative of the second derivative. But the second derivative is minus by. So this is minus b dy dx, or minus by prime. So because y can be differentiated twice, it has a first derivative and a second derivative. But that means it has a third derivative. And what's the fourth derivative? Well, the fourth derivative, if it exists, is the derivative of the third derivative. But this is the third derivative. So that's minus b y double prime. So the fourth derivative exists. Is there a fifth derivative? Well, this would be the derivative of the fourth derivative. But this is the fourth derivative.
Inception.
Yes, is there a question? Okay. This is the fourth derivative. So this is minus b times the derivative of y double prime. That's minus b times the third derivative. And this is the third derivative, minus by prime. So this is minus b times minus b squared, y prime. So the function has a fifth derivative. Now this is fun. The sixth derivative is the derivative of the fifth derivative. That's the derivative of b squared y prime. That's b squared y double prime. The seventh derivative would be the derivative of the sixth derivative. That's the derivative of b squared y double prime. That's b squared times the derivative of the second derivative, which is the third derivative. The third derivative is minus by prime. So we get minus b cubed y prime. So continuing, we see that y equal f of x, a solution of the differential equation, is infinitely differentiable. That is, the nth derivative of y exists for all n. Has a first derivative, second derivative, third derivative, and so on. In fact, if you look at the derivatives we've gotten so far, let's see, what do we have? We had y double prime. The fourth derivative was minus b times, oops, I should have kept on going. The fourth derivative is minus b y double prime, which is minus b, and by the differential equation, y double prime is minus by. So this is minus b times minus by is b squared y. The sixth derivative was b squared y double prime. That's b squared minus by is minus b cubed y. If I had computed the eighth derivative, that would be minus b cubed, the second derivative, which is minus b cubed times minus by, which is b to the fourth y. And it'd be easy to prove by kind of mathematical induction. So this is the table that I had computed completely. Y to the 0, that just means y. The 0th derivative of a function is just a function. The second derivative is minus by. That's the differential equation. The fourth derivative is b squared y. The sixth derivative is minus b cubed y. The eighth derivative is b to the fourth y. In general, for all integers n, the 2nth derivative of the function is equal to minus 1 to the n, b to the n times y. For example, when n is equal to 4 and you have the eighth derivative, this is minus 1 to the fourth, which is 1, b to the fourth y. So we have this formula for every even number derivative of the function. And y to the 2n minus 1, if you just looked at the data and see what we got, you would get minus 1 to the n minus 1, b to the n minus 1, y prime. So you can express all derivatives of the function y in terms of y and y prime. And we can also evaluate these derivatives at 0. Well, now it's clear. So for the function y equals f of x, where f of 0 and f prime of 0 are equal to 0, what the 2nth derivative evaluated at 0 is minus 1 b to the n, y at 0 is 0. And every odd derivative evaluated at 0 is minus 1 to the n minus 1 b to the n minus 1 y prime of 0, which is 0. So in fact, for the solution of this differential equation, it has the amazing property that every derivative evaluated at 0 is equal to 0. So what does that tell us about the Taylor polynomial? So, as I always say, One of the unfortunate things about mathematics is if a course is a prerequisite, it means you not only took the prerequisite course, but you learn it. You learn. It's not like, I mean, you can study 19th century literature without having read 18th century literature. But you can't do calculus 2 without calculus 1. And you can't do differential equations without calculus 1, 2, and 3. This is from calculus 2. We have the Taylor polynomial of a function on an interval. So you take some number c and look at the closed interval from minus c to c, and the Taylor polynomial of degree n of this function we'll call it h of x. So the Taylor polynomial of a function f of x of degree n. I just want to follow the same notation that the book uses. The book calls this h of x. So you know from calculus 1, this is summation let's say k goes from 0 to n. The kth derivative of the function evaluated at 0 over k factorial times x to the k. So this is a polynomial in x plus a remainder. So we're going to take the Taylor polynomial of f of x on this closed interval of degree 2n minus 1. So we're writing this polynomial degree 2n minus 1 plus this remainder term. And that's just the general formula for a Taylor polynomial. So given any function which has, in this case, 2n minus 1 derivatives, or 2n derivatives, you take the kth derivative at 0 divided by k factorial times x to the k. H of x is equal to this plus this error term. And the important thing, the only way you can, what makes a Taylor polynomial useful is if you can estimate the error term. So you know how closely the polynomial approximates your function. Now, in our case, if f to the k if every derivative is 0, then in fact each of these terms is 0, and h of x is exactly equal to the error term. Sorry, I'm not. I made everything I said is correct except for one bit of notation. So let's just go back and remember what it is we're trying to prove. We're trying to prove the uniqueness theorem, that if you have a differential equation y double prime plus by equals 0, and if you have two solutions, f of x and g of x, that solve this equation, and they take on the same value at 0, and their derivatives take on the same value at 0, then we want to prove that f of x equals g of x. That's exactly the same thing as proving that f of x minus g of x is 0 for all x. And we're going to let h of x be this difference. So h of x is f of x minus g of x. And what we want to prove is that h of x is 0. So I'm going to compute the Taylor polynomial of this function h of x, which is f of x minus g of x. So this should be an h here. So this is just like a little reminder. H of x equals f of x minus g of x. The kth derivative of x is 0. Sorry. H of x is f of x minus g of x. H of 0 is f of 0 minus g of 0 is 0. H prime of 0 is f prime of 0 minus g prime of 0 equals 0. And the kth derivative at 0 is equal to 0 for all k. Okay. So every derivative is equal to 0, not just the 0 in the first derivative. This is the Taylor polynomial, and this is the remainder term. So I should say, because the kth derivative at 0 is always equal to 0, h of x is equal to the remainder term. What is the remainder term? So one of the things that's proven back in calculus, at least it's supposed to be proven, is that the remainder term for any n, e sub n, you would go out to n, e sub n of x, is bounded as follows. It's less than or equal to m x to the n over n plus 1 factorial. Let me just write it like this. Well, this is the way it's usually proven in the textbooks. And little m x to the n over n plus 1 factorial, where the n plus first derivative of the function h is bounded above and below by little m and capital M on the interval from minus c to c. And we're letting n be 2n minus 1. So let me just replace this by 2n minus 1, 2n minus 1, 2n minus 1. And then this is the 2nth derivative. Okay, so you take a function h of x. It has 2n derivatives. You can write down on an interval from minus c to c. It's a finite closed interval. So 0 is in the middle of the interval. And if we look at the Taylor polynomial for this function centered at 0, the polynomial is this polynomial of degree 2n minus 1 with coefficients, which are the derivatives of the function at 0 divided by some k factorial. But for our function, if it's a solution of this differential equation satisfying these initial conditions, all these derivatives are 0. So h of x is just equal to this e sub 2n minus 1 of x. And e sub 2n minus 1 of x is a function which is bounded above and below by m times x to the 2n minus 1 over n plus 1 factorial, where m is like an upper bound for this function on the interval. And what is h to the 2n of x? Well, we computed the 2nth derivatives a moment ago. The 2nth derivatives were minus 1 to the n, b to the n, y. So minus 1 to the n, b to the n, times y, which is h of x. So suppose that h of x in absolute value is less than or equal to m on the interval from minus c to c. This is a continuous function on an interval. It has an upper bound, and we'll just call the upper bound m. It should be 2 n's.
Professor.
Yes.
So in the first inequality, when you have m and then the fractions, so on the left it's m and on the right it's n.
Oh, sorry. So this is a lowercase m. This is just supposed to be a lower bound for the function, but actually I can make it easier and just write this as the absolute value of this is less than or equal to capital M. I just want to remember the right form. Yeah, this should be a 2n. Just makes it a little bit easier. So, so this function e sub 2n minus 1 of x, again, this is all written down in the notes that I gave out. I mean, in the pages from the book by Apostle, it's the same thing, except in the book it's legible. This error term is bounded by m x to the 2n over 2n factorial. And if you're looking on the interval from minus c to c, so the absolute value of this nth derivative is the absolute value of this. This is less than or equal to b to the n, the absolute value of h of x, which is at most m, and x, yes. So e2n minus 1 of x in absolute value is less than or equal to m. On the interval from minus c to c, x is at most equal to c. So this is b to the n, m, c to the n, c to the 2n, over 2n factorial. So b to the n, m, c to the n, over 2n factorial. So So this is like BC to the n m over 2n factorial. So what you have to know is a limit, which comes from Calc 2, Calc 1 probably. If you have an nth power over n factorial, this goes to 0 as n goes to infinity. So the upshot of this, I think I'll do this again on Wednesday just to make it maybe a little bit clearer, is that h of x is equal to e sub 2n minus 1 of x for all n. And e sub 2n minus 1 of x goes to 0 as n goes to infinity. So this means that h of x is equal to 0. Because this thing is getting smaller and smaller with n, but it doesn't depend on n. It gets arbitrarily small. So let me just say this proves uniqueness.
Oh, sorry.
That's all right.
I keep forgetting to turn off the microphone. Sorry.
No. So this is hard. This is why, I don't know, there are a couple of students who are in this class. I don't know. Let's see, wait a minute. Yeah. So if you're like a chemistry, physics major, maybe you have to solve differential equations to solve problems in chemistry or physics. But in mathematics, you have to prove things. So the mathematicians tell you that a solution is unique, and that's good enough for the physicists. But the mathematicians need to actually know why that's true, be able to prove it. In fact, when we have Maple, you'll be able to type almost any ordinary differential equation we have into Maple, and in a microsecond, Maple will give you the answer. So, I mean, it's important to know by hand how to solve these equations, but in practice, most equations that come up are too hard to solve by hand, and you need a computer to do it for you. But what justifies the computer's work is the fact that there are theorems that underlie how rapidly things converge and so forth.
Yeah.
Anyway, so this is a theorem in mathematics that for this very special second order homogeneous linear differential equation, every solution has one and only one solution. Solutions exist, and once you fix the boundary condition, the solutions are unique. So, and then you can carry this over to proving the uniqueness, not just for the differential equations where a is equal to 0, but also when a is not equal to 0. You get all solutions. Okay. All right.
Professor.
Yes.
This is only applied for homogeneous, or is an exception for non-homogeneous?
So for constant coefficients, this is there's also uniqueness for non-homogeneous. Once you go to equations that are not linear, which is most of the, I mean, in mathematical physics, there are very good approximations to problems using linear differential equations. But they're approximations, and the actual differential equations tend to be nonlinear. And nonlinear equations often have multiple solutions, not unique solutions. And in most cases, you can't solve them. They're just, they're impossible to solve. They have, you can prove they have solutions, but you don't know how to write them down. And so there's a huge industry. I mean, a lot of people make a lot of money in corporations using computers to solve nonlinear equations numerically. And for a lot of equations, so a lot of applications. So in physics and engineering, fluid dynamics is extremely important. This has to do with turbulence in water, in the air, planes crash and bridges fall down because of some kind of nonlinear behavior. And this is really difficult. This is, I mean, a huge amount of work is still being done trying to understand various kinds of nonlinear differential equations, ordinary and partial differential equations. And we're going to look at that when we get back to looking at PDEs, but you can't do PDEs without a little bit of knowledge of ODEs. That's what we're doing for these couple of weeks. I mean, factually, for the month of September is devoted to ordinary differential equations. And October, November, December, we're back to partial differential equations.
Are we going to do on Wednesday the Bernoulli second order differential equation?
Was that one of the homework problems?
Yeah, but basically it's just that example when it's essentially not homogeneous. So you just have a, on the right side of the equal signs, it's not zero.
Which problem number was that?
It's number 14 and...
Yeah, 13, number 13.
No, 14 in the homework number 2. Oh, it's a first order, but on the right side it's 2.
Yeah, homework 2, number 13 and 14. All right, so, yeah, so that's, yes. Well, I will make a point of going over that the beginning of class on Wednesday.
Mm-hmm.
Yes. So that's a nonlinear equation that you, yes, that we can still solve. All right. All right, so if there are no more questions, we will quit for the day. There is a homework due on Wednesday. It is homework number 2 on pages 311 and 312, numbers 1 through 6, 13 and 14.
What about homework 3?
Homework 3 is due a week from, oh, sorry, 16th. Yeah, sorry, I have it backwards. Homework 3 is due on Wednesday. That's page 328, 1 to 6, 11, 13, and 14. Yep. Yep. That's the homework that's due on Wednesday.
Okay,
I will
so
email out later today also the current revised extended lecture and homework schedule, which covers the next few weeks. In fact, it'll cover up until the end of September.
okay.
Okay, that's it for today. I will be back on Wednesday. All right, bye everybody.
Right, have a good day.
Thank you, you too.
Really.